Good day, ladies and gentlemen. My name is Chadi Heeralall. My project leader is Mr. Ayanda Nzo, and my project is investigating thermal insulation for a metal sheet house. Here is a brief outline of my presentation, starting with a brief background, problem statement, objectives, the final concept used to solve the problem, the experimental process, experimental results, verification, validation, experimental verification and validation, summary of my results, conclusion, real-world applications, and time for questions at the end. In South Africa, roughly 5 million people live in informal housing in the form of metal sheet houses. These houses inform metal sheet houses known colloquially as shacks. These shacks are mostly made of corrugated iron sheets, also known as CGI sheets. The metal used in these shacks is very dense and is a good conductor of heat. As a result of this property, any heat that a metal sheet house is exposed to will be quickly absorbed and transferred outside the home. Metal sheet house residents have a rough average monthly income of around 2,113 rand. This is an important figure to consider as it greatly limits what they can afford to spend their money on in future, thus limiting what building materials and food and building materials they can potentially purchase in the future. Insulation. Insulation is a term used to describe a material that creates a barrier for the conduction of heat between two bodies. Insulation does not require any electricity to function and can be used to keep any home cool in summer and warm in winter. Studies done by the University of Pretoria have shown that applying thermal insulation to the walls of a home can improve thermal comfort by creating a significant temperature difference between the outside conditions of a home. Waste materials as insulation. To improve the overall comfort of shack residents, the insulating properties of readily available waste materials will be investigated. These materials can be easily found and recycled and repurposed from most major landfills and rubbish dumps. The most common waste material types have been determined and have been tabulated in the next slide. Here you can see the most common waste materials being paper, PET, plastic, and cardboard. Their thermal conductivity as well as advantages and disadvantages are all compared to corrugated iron, which is the current building material used in metal sheet houses. As you can see, the thermal conductivity for paper, plastic, and cardboard, the waste, are all significantly lower than that of corrugated iron. Thermal conductivity is a measure of how well a material can conduct heat, where high conductivity indicates a good conductor and a low conductivity indicates a poor conductor. The problem statement. Many low-income South Africans live in metal sheet houses. The thermal properties of the metal used to build these houses make temperatures inside uncomfortable. Insulating the home would help alleviate all these temperature issues. However, standard home insulation is too expensive for metal sheet house residents due to their already limited budget. There presents a need to provide shack residents with effective home insulation using readily available materials. Waste materials possess thermal insulating properties and can be easily recycled and repurposed. Can waste materials serve as effective insulation for metal sheet house residents? The objectives of the study started with research to identify readily available waste materials, experimentation to determine the thermal response of an uninsulated sheet of corrugated iron, to determine the thermal response of an insulated sheet of corrugated iron, and to test the effectiveness of the waste material insulation overall. Results and analysis to determine the thermal properties of the waste materials tested, to compare the experimental results, to compare the experimental values to literature to verify the results, to validate the obtained results, and to compare and to select the two most viable materials between of the materials tested. Here you can see a simplified conceptual schematic of the test bench to be designed, that was designed. Point 1 indicates the infrared heat lamp used. Point 2 is the corrugated iron sheet. Point 3, 4, 5, and 6 respectively are the points where calibrated type K thermocouples we placed in order to measure the temperatures of these particular items over the testing period, where point 3 is the temperature of the heat source. Point 4 is the temperature of the bottom of the corrugated iron sheet across the material's thickness. Point 5 is the temperature of the top of the corrugated iron sheet, which is the part that is directly exposed to the heat source. Point 6 is the temperature of the heat sink. Point 7 is the heat sink itself. The test bench will provide a known heat transfer value Q, hold the corrugated iron sheet and waste materials in place, keep outside convection, conduction, and radiation from affecting the flow of heat on the waste materials, and include a heat sink to create a low temperature region to allow for heat to flow throughout the system. Here are some detailed CAD models of the final test bench design. Here are some detailed drawings of the final design. And here is the final concept that has been built. This an experimental test bench was built to determine the thermal response of different waste materials as insulation. The frame was made from plywood and coated in a layer of ceramic fiber insulation. A 250-watt infrared heat lamp was used as the known heat source throughout the experiment. An insulated box design was chosen to completely insulate the test materials from the outside environment, thus preventing external sources of heat from affecting the test results. The experimental process starts with specimen preparation, where layers of waste are placed on top of one another and cut to fit the size of the test material corrugated iron sheet. The volume of the waste material will remain constant throughout testing for all three waste materials, with a constant thickness of 0.47 millimeters. This is the same thickness as the corrugated iron sheet used throughout testing. The materials are set up in two configurations. Configuration 1, the specimens are layered on top of one another and glued together, and in configuration 2, the specimens are layered on top of one another and held together using layers of cling wrap. Here you can see the paper specimen, the cardboard specimen, and the plastic bag specimen made up of PET plastic. The following apparatus and materials were used throughout testing, starting with the designed experimental test bench, a temperature logger, 4 calibrated Type K thermocouples, ice bricks as the heat sink, a corrugated iron sheeting, an infrared heat lamp, and waste materials paper, PET plastic, and cardboard. The experimental process begins as follows, starting with specimen preparation. This has already been discussed. Step number 2 is specimen testing, where the specimen is placed inside the experimental test bench at point 2. Step number 3 is to apply thermocouples to point 3, 4, 5, and 6 respectively, using drilled holes at the side of the test bench. Step number 4 is to measure, to monitor and record temperature values of the thermocouples until steady state conditions have been reached. Step number 5 is to repeat steps 1 through 4 for each material type and configuration. Step number 6 is data analysis, using the recorded temperature values, calculate the temperature difference across the material thickness, and calculate the experimental thermal conductivity of each material type and configuration. Step number 7 is comparison, to compare the experimental values to known values from literature to verify the overall experiment. Okay, the experimental results. The experimental results for the plain corrugated iron sheet, paper waste, cardboard waste, and plastic waste have been graphed here. The temperatures on each side of the material thickness can be seen here, where the top surface is the side that is directly exposed to the heat source, and the bottom surface is on the other side of the material thickness. As you can see, this is the top and bottom surface temperatures of the plain corrugated iron sheet. Over time, this served as the control throughout the overall experiment. As you can see, okay, the rise in temperatures due to the test bench itself being switched on and the system itself heating up. The values highlighted in yellow are points where temperatures remained mostly constant, and these were interpreted as steady state in the mathematical model. The drop in temperature is due to the test bench itself being switched off and the system cooling down. As you can see, there is a very almost negligible difference between temperatures across the material thickness. This is due to the thinness of the plain corrugated iron sheet, as well as the high thermal conductivity of the metal itself. The average temperature differences across the material thickness for each material type and configuration have been tabulated here and summarized. The table on the left is configuration 1 being the non-cling wrap configuration. The table on the right is configuration 2 being the cling wrap coated specimens. The average temperature difference across the material thickness, the delta T 1, 2 over the corrugated iron sheet. As you can see, those remain constant. This served as the control throughout the experiments. The average temperature differences across the material thickness for the configuration 2 is significantly higher than that of configuration 1. This is due to the added thickness from the cling wrap itself, as well as the inherent thermal insulating properties of the cling wrap itself. From this, we can conclude that configuration 2 does produce higher temperature differences out of the two configurations and is a more viable insulation setup. Experimental verification. The experimental values for each material type and configuration were then used to determine the experimental thermal conductivity of each material type and configuration. These values are then compared to known values from literature to verify the overall experiment. Assumptions made during verification. The corrugated iron sheet is treated as a flat piece of metal. No outside convection, conduction, or radiation is considered. The thermal conduction will be the main focus in the mathematical model. The effect of glue and cling wrap on the specimens will be ignored. Only temperature values at steady state conditions are considered valid for the mathematical model used, and an efficiency of 92% is assumed for the infrared lamp. Experimental validity. To check the reliability of the experimental method, multiple experiments are conducted on the same material type and configuration and compared to one another. The experiment was then validated by calculating the standard deviation between each experiment and configuration. Here you can see the experimental verification and validation for the plain corrugated iron sheet. The experimental thermal conductivity was calculated in the table to the left, the theoretical and compared to the theoretical thermal conductivity from literature. As you can see, there is a percentage error of around less than 12% for each test conducted, with a standard deviation of much less than 1. This very low standard deviation indicates very low variance between each testing set, indicating that the results can be considered reliable. Here is the experimental verification and validation for the paper waste. The subtable on the left is for configuration 1. The subtable on the 2 is for configuration 2. Again, the percentage errors are quite low for both configuration 1 and configuration 2, and the respective standard deviations are all much less than 1, indicating again low variance between each testing set. The experimental verification and validation for the cardboard waste follows the exact same format as for the previous slide. Again, low percentage errors and low standard deviations. Here's the verification and validation for the paper waste. Same format as previously discussed. Low percentage errors and low standard deviations. Summary of the results. In summary, the experimental data produced by the test bench closely corresponds to data obtained from literature. This confirms that the experimental test bench is a viable means of testing insulation materials, producing a less than 12% error for the corrugated iron sheet and a less than 10% error for most of the waste materials, and as well as less than 1 standard deviation between each test specimen. Adding layers of waste material as insulation of equal volume to a sheet of plain corrugated iron provided significant temperature differences of up to 5 degrees Celsius. Configuration 2 is clearly the better insulation option, especially for the plastic and cardboard materials. Conclusion. In this project, I was required to identify common waste materials and determine their viability as insulation in a metal sheet house. To test the viability of these materials as insulation, an experimental test bench was constructed. After applying the waste materials in the test bench, testing revealed that the addition of waste materials as insulation provided significant temperature differences across the material's thickness compared to the plain corrugated iron sheet. The plastic bag and cardboard in configuration 2 have the lowest thermal conductivity of these 3 materials and produce the highest average temperature differences across the material's thickness. This makes plastic bags, PET plastic, and non-corrugated cardboard the most viable insulation materials of the 3 materials tested. Real-world applications. The thermal conductivity of cardboard and plastic were then compared to industry-standard materials such as EPS and isoboard. As you can see, the average thermal conductivity of the expanded polystyrene and isoboard are significantly lower than that of cardboard and plastic, indicating that they are still the more effective insulation options. However, waste material-based insulation is still quite viable due to its already low thermal conductivity and its low cost to implement, which is important for the metal sheet house residents, who this is actually for, as it would be very cheap to find. Waste material costs little to nothing to recycle and repurpose. Thank you. Any questions?